The authors propose a novel approach for understanding the periodic structure and semantics of motion datasets, independent of the morphology and skeletal structure of characters. They present a phase manifold consisting of multiple closed curves, each corresponding to a latent amplitude, learned using a vector quantized periodic autoencoder, VQPAE. This manifold enables timing and semantics alignment between motions from different characters, without any supervision or paired data. The VQPAE decomposes motions into a 1D phase and discrete amplitude vectors, forming a disconnected 1D manifold where each component is an ellipse corresponding to a discrete amplitude vector. The possible choices of amplitudes are learned through vector quantization, similar to a clustering process. The discrete amplitude vectors serve as a narrow bottleneck to regularize unsupervised learning of semantic motion clusters. The authors demonstrate the capability of the phase manifold for motion alignment, retrieval, transfer, and stylization. They learn VQPAEs from both a human dataset and a dog dataset with a shared codebook, and show that the learned embeddings are both timing and semantics aligned between the two characters. This highly structured and aligned phase manifold opens up new possibilities for motion data organization and integration with existing motion synthesis pipelines. The key contributions of this work include a novel phase manifold designed for both timing and semantics alignment, demonstrating the use of narrow bottlenecks and intrinsic structure of motions to achieve alignment among heterogeneous datasets without supervision, and applications with an improved motion matching framework on the phase manifold for motion retrieval, transfer, and stylization. Here is a combined summary of pages 58 of the research paper. WalkTheDog is a method for cross-morphology motion alignment via phase manifolds, which learns a common phase manifold among multiple VQPAEs by sharing the codebook A and optimizing a loss function that combines reconstruction losses and vector quantization loss. The codebook is utilized effectively by adapting a reinitialization technique to reinitialize less frequently used entries. This method can learn a common phase manifold with only a shared codebook A and no additional supervision, unlike existing methods that require partially specified skeletal topology correspondences and additional implicit supervision. Frequency-scaled motion matching is proposed to solve the problem of timing and semantics misalignment in motion matching, allowing for more responsive and smooth motion transfer. The learned phase manifold is used to model different character topologies, including biped and quadruped, without extra class-specific designs. The effectiveness of the method is demonstrated on several datasets, including dog, human locomotion, and MoCA, and shows its potential for improving motion matching, motion transfer, and motion stylization. The authors evaluate their method by examining the average pose at each point of the manifold to verify its alignment effect and propose training a small MLP for each dataset to minimize the pose loss. They also evaluate their method on different settings, including human dog and stylized settings, and show that it is possible to learn a shared latent space for multiple datasets with different characters. An ablation study is conducted to investigate the impact of codebook size and reinitialization of the amplitude on the performance of WalkTheDog. The results show that a larger codebook size improves expressiveness but reduces the percentage of embeddings in the dataset that lie on a shared connected component. The limitations of the current framework are discussed, including the requirement for carefully picking the right codebook size to balance between expressiveness and overlap among datasets. Future research directions include automatically learning the size of the codebook, filtering out motions that are not semantically similar, and exploring the possibility of generating new motions from the phase manifold. WalkTheDog, a novel approach for cross-morphology motion alignment, leverages phase manifolds to address challenges in motion transfer between characters with different morphologies. This method aims to preserve both the semantics and timing of motions, drawing inspiration from physics-based character skills, deep reinforcement learning, and image synthesis. By disentangling phase and amplitude, WalkTheDog generates motions that combine the semantics from the amplitude input and the timing from the phase input, resulting in more plausible and characterized motions. The WalkTheDog framework employs a phase calculation module to compute the phase manifold, using the equations presented by Mason, 2022, to calculate the phase from a one-channel signal and relative timing. The motion matching algorithm retrieves the motion sequence from the database using phase embedding as the control signal, iteratively finding the closest match in the database and outputting the corresponding motion sequence. The pose descriptor used is a simple normalized joint position, ensuring a smooth transition between different replays. The authors provide an overview of the datasets used in their experiments, including dog, human locomotion, mocha clown, mocha ogre, and mocha princess, with training times varying from 40 minutes to 2 hours and 40 minutes. The network architecture consists of a convolutional encoder and decoder with a shared architecture, as well as multiple MLPs for different tasks. The hyperparameters used include a learning rate of 1 × 10⁻⁴, batch size of 32, and the atom optimizer, with joint velocity in the local coordinate of the character as the input feature. The paper references various works, including skeleton-aware networks for deep motion retargeting and periodic autoencoder explanation and addendum, among others. WalkTheDog has the potential to revolutionize the field of computer animation and beyond, enabling more realistic and engaging character movements in various applications. Further research into motion phase manifolds is needed to enhance the realism and efficiency of motion transfer algorithms.